In this video, we're going to be looking at relaxation. There are two types of relaxation process. T1 relaxation, also known as spin lattice relaxation or longitudinal relaxation, and T2 relaxation, also known as spin-spin or transverse relaxation. Let's start with T1 relaxation. That's the process whereby atomic nuclei come to thermal equilibrium in a magnetic field. And in the case of the Terra Nova apparatus, that would naturally be the Earth's magnetic field. Of course, to come to thermal equilibrium requires some sort of an energy exchange process with a thermal reservoir. And the thermal reservoir in this case is really the thermal energy of the molecules that contain the atomic nuclei in their tumbling and in their vibration. That's really why it's called spin lattice relaxation. In the case of a solid, the vibration would be the atoms or molecules on the lattice. But we use exactly the same name when we're talking about liquids or any other state of matter. Why is it called longitudinal relaxation? Well, in coming to thermal equilibrium in the Earth's magnetic field, the state of the magnetization that's achieved is along the magnetic field, longitudinal with the field. To demonstrate T1 relaxation, we're not going to look at the process of coming to equilibrium in the Earth's magnetic field. Instead, we're going to look at the process of coming to equilibrium in the pre-polarizing field that's produced by this coil on the Terra Nova apparatus. What we're going to do here is to perform a number of experiments where in each case we'll vary the duration of the polarizing pulse before we start the nuclear magnetic resonance experiment and see how big the magnetization that we've created is. Now, the process of coming to thermal equilibrium really depends upon the difference between the current state and the thermal equilibrium state. And of course, as always, when a rate of change depends upon a difference like that, it's going to be an exponential process. So T1 relaxation will be an exponential process of coming to the equilibrium magnetization state. Because it takes a little while to do these separate experiments with different duration pre-polarizing pulses, I've done this experiment in advance and stored it in the computer. And I've carried out the T1 experiment on this sample of water. So let's go and look at what we've obtained here. Here we see one of the free induction decays obtained for a particular duration polarizing pulse. When we Fourier transform that, we get the spectrum. And the area under that spectrum tells us about the amount of magnetization that remained after that pre-polarizing pulse. On the right-hand side here, we've plotted those areas as a function of the duration of the polarizing pulse. And you can see that the magnetization starts off low, but gradually builds up with increasing duration of polarizing pulse to reach a plateau value at around about 5 seconds. In fact, we've fitted a single exponential growth to the plateau on this data. And the decay constant associated with that exponential is 2.1 seconds. That's a pretty normal T1 value for water molecules. Next, we're going to look at T2 relaxation, or spin-spin or transverse relaxation. It's called spin-spin relaxation because it involves exchange of energy between the spins, a process by which the spins get out of step with each other and cause this irreversible loss of magnetization that cannot be recovered in a spin echo experiment. It's also called transverse relaxation because it leads to a decay of that transverse magnetization precessing in the spin echo experiment. Again, I performed this experiment in advance using the water sample. Here we see the train of echoes dying away with time due to this irreversible T2 relaxation. In each case, the echo is Fourier transformed to get a spectrum, and the area under that spectrum tells us about the size of each individual echo. And on the right-hand side, we see the areas of those spectra obtained at different echo times plotted as a function of time. Again, the scale goes from 0 out to about 5 seconds. And here you can see the decaying away of the echo amplitudes with increasing time. Once again, we've fitted a single exponential to that data. And the time constant for that in the case of T2 is around about 1.6 seconds. Again, a very typical value for water molecules.